is I want to go back in and look at our chickens again. Hopefully that makes sense. So I want to go back in and look at our chickens. And we were analyzing Marge, Bertha, Mary, and Nancy last time. And we were trying to figure out, on average, how many girls am I going to get per flock of 4 that I buy at the store? What's the likelihood they're all girls? What's the likelihood they're half girls and all these things? And last class was awesome. I mean, almost the entire day was spent filling up the board with distributions of the chickens. And that was great. That was great. That's going to get exceptionally tedious very, very quickly. Exceptionally tedious very, very quickly. The good news is you don't have to do it manually anymore. I mean, you don't have to. Because what these chickens are an example of a binomial random variable. Now, we talked about the idea of random variables and their distributions last time. This is a specific kind of random variable. Not all random variables are binomial. This is like a subset. So you can think of it like comparing it to all foreign languages. The last lesson was about all foreign languages in overview. Now we're talking just about, say, Spanish. Just one language of the many. They all have something in common, that they're all languages, but this is a very specific kind of language, and this is a very specific kind of random variable. There are hundreds of these things. Just so you know, there are hundreds of these things with special names like binomial, multinomial, chi-square, normal T, F, Pearson. I stripped it down to 2 for the remainder of our class together. Because those 2, number 1, are the ones you're going to see the most in the world when you read Gallup polls and things like that. And number 2, those of you going to 244, those are the ones we start with and spend about half the class in. So it makes the most sense to focus on those 2 rather than try to put a bunch of other ones in. I was riding home from work yesterday, I got a flat tire on my bike, which I was just talking to somebody, I'm like, man, I haven't gotten a flat this year. Boom, 3 days later I get a flat. And I saw Don, the other stat instructor, working with the student yesterday. I'm like, yep, Poisson! And I kind of shook my wheel, I was walking it in to change it. And I shook it. I said, Poisson, which is called the rare event law. And it's a distribution that explains things like getting flat tires on your bike. Like the average number of flats you could expect per unit time. And I was due. I mean, essentially I was due. I hadn't gotten a flat in long enough, and my average of 1 or 2 per year wasn't being recognized. And then there was one day I got 3. Last spring? Yeah, last spring I had 3 flat tires in one day. Which is to be expected if I ride my bike long enough. Right, that's the whole thing. It's to be expected if I ride my bike long enough, and I've ridden it for almost 20 years commuting. So one of these days I'm going to get 8. It's just a matter of if I live long enough to see it. So, make sense? So this is a binomial. So let's talk about what makes the chickens a binomial. What makes the chickens a binomial? There's three main things. The first thing is you have to have a fixed number of tries. So I sent Max into the store. And I said, Max, go get some birds. And in particular, how many did he go in and get?
4.
He got 4, because that was the deal. In Bend, you cannot legally have more than 4 in the city limits. So I said, okay, go in and get 4. Let's max out the city limit law. Now my neighbor's walking in my backyard. Holy crap, it's like a farm back here. Beehives, freaking chickens, rows of corn. Well, not yet. Soon. Anybody get asparagus coming in their garden yet? Asparagus? Starting to pop up? Anybody grow asparagus? It's a perennial, one of those nice perennial garden crops you can grow in Bend. You don't have to plant it every year. We got 5 or 6 stalks coming. Good stuff. Anyway, the chickens are binomial, and for the first of 3, because I sent Max in to buy 4 chicks, we decided they were independent yesterday. Do you remember why we decided that the trials were independent of each other? Remember why we decided? There were so many that we were drawing from, and so few that Max was taking. So many we were drawing from and so few that Max was taking, so arguably they're independent trials. Arguably. Not literally, but arguably they're independent. There's no reason to think that we're changing the proportion of the 90-10 because Max is pulling a few chicks out of these huge bins full of marshmallow peeps. Cool? So that's the first thing. Fixed number, independent trials. Fixed number, independent trials. We'll see another couple examples of this momentarily. Okay? Number 2, this is what makes it binomial. Binomial. Okay? The binomial part makes it, each time you perform the experiment, one of 2 things can happen. And if one happens, the other one can't. If one happens, the other one can't. So since the chickens are either male or female, that's what makes it binomial. That's what makes it binomial. If I was interested in what kind of chick Max got, it would be multinomial. because there were like 5 or 6 different kinds of birds in the store at that time. Like there were sex links, there were Orpingtons, there were Americanas, Delawares, Plymouth Barred Rocks, a couple of them, ducks, turkeys. I mean, there's a bunch of different chicks. So if I was interested in what kind of chick he got, then it's a different story. It's not binomial anymore because you've got more than 2 outcomes. But since there are only 2 outcomes here, that's the bi in the binomial. You can also have tri and multinomial. They're fun too. We'll deal with them in 244. We'll test the iPod randomizer. See how random an iPod actually is, and we'll also test the M&M color distribution that they tell us should be in an M&M bag of M&Ms. So stuff like that. Cool so far? And then last but not least, and these kind of go, 3 kind of goes hand in hand with 1 and 2. Since they're independent, the probabilities don't change from trial to trial. So the chance of a girl is always 90%, the chance of a guy is always 10%. That doesn't change as we move from trial to trial. I thought I fixed this before. Yeah, we can do that. Get the shadow out of there. Yeah, okay. And we utilized that a lot last time by multiplying those together, 0.1, 0.1, 0.9, 0.9. Of course, the interesting part about it was what number you had to multiply in the front to get the correct sum of the probabilities, to sum up to 1. And I love the fact that we struggled with that for about an hour. That was great. That was time well spent, in my opinion. It's also time well... Okay, let me see how I can phrase this right. It was time well spent on Monday. It's time better saved by not doing it manually from here on out. Especially because of one of the questions I'm about to ask you, based on chickens. Technology is a much better friend for us than manual calculation of these distributions. I mean, imagine you had 1,000 chickens. 1,000 chickens, right? Figuring out those coefficients. And you might say to yourself, well, that's ridiculous. Why would I have 1,000 chickens? And I say, you wouldn't. But you will often, if you're on a Gallup poll, have 1,000 respondents on the poll. And a respondent on a Gallup poll is exactly the same as picking a chicken out of these bins. If you're asking them to say, do you approve or disapprove of Congress? That's binomial. You either do or you don't. It's a fixed number of 1,000 trials. But then you have to figure out this distribution, and you don't want to do that manually because it's ridiculous to do it manually. That's why I give you the program. There's a program actually does it for you. So I want to revisit that program to make sure you guys know how to use it. Go ahead, Jada.
I need it in my...
Okay. Does anybody else need the program that we shared?